We're getting started in another video, another statics problem I have for you here. This one is about centroids and moment of inertia, area moment of inertia. So let's get started. Beam designer has to choose between an I-beam here and a rectangular beam here. The cross sections of the beams are shown. The width of the stem and the flanges in the I-beam is 1 inch. Oh, that means the thickness here. I'm just going to write as t equals 1 inch. So part 8 says locate the centroid of the cross section and determine the second moment of area of the I-beam with respect to its centroidal axis. I'm trying to think here. Locate the centroid of the... Why it's only asking for that. Locate and determine... Oh, okay. So we essentially need to find the centroid of the axis is going to be located, or of this cross section is going to be located here on this axis XC. And so we need to solve for what that is. So I'm going to go ahead and draw another thing here. And we can label this as, let's say YC maybe. Something along those lines. And we can label this maybe as X prime. This is just to help us see what's happening exactly. But what we need to know for finding the centroid is... well, this centroid here, even though the axis is XC, it's actually going to be at a distance YC, like I drew here. So YC is going to be equal to the sum of YC times A over the sum of A. Essentially, we'll split this off into multiple different shapes, and we'll take the centroids of each of those shapes in relation, or the distance in relation to this X prime that we have here, multiply that by their areas, and then divide it by the entire area of the whole thing. And that's how we'll find the centroid of the entire shape. So to do that, the easiest way is to make a table. And so that should be your first instinct in these problems. Even if there aren't too many shapes, it's always helpful to have a table and organize what's happening and label your shapes. So we've got the table, we'll label our shapes, and we'll split it off. So this is pretty easy. An I-beam right here, it should have 3 rectangles, should be the shape. So we'll have 2, and 3. 1, 2, and 3. So for shape 1, 2, and 3, we'll need to find first the area, probably the easiest thing to find, and then we'll say YC for each individual shape. And then we can take YC times the area, and that should be all we need to know for that. This table is going to be bigger though. We're going to expand upon it, but for now, for the time being, we are just going to find this information here. So that for the area for shape 1, it's 10 inches by 1 inch thickness. So that's going to be 10. And we'll go ahead and write in inches squared for the area, because it's in inches. And so the area for 2 is going to be 10 times the thickness again is 1, so 10. And then for the bottom, it's going to be 5 times, again, the thickness 1. So it's just going to be 5. The total area is going to be 25 inches squared. Now we need the centroids. The centroids for rectangles are always going to be in the middle. So if the thickness, let's take a look at shape 1 here. The thickness is 1 inch. So the centroid is going to be 0.5 inches from the top. So I'll label that 0.5. And we'll have our little dot there for the centroid. So 0.5. So we'll take this entire distance, which is 1 inch plus 10 inches, plus another 1 inch is 12 inches. And we take it down 0.5 inches is 11.5. So YC for 1 is 11.5 inches. And this is going to be inches cubed. For 2, don't get distracted by this little dot on the centroid I drew here. The centroid of this beam itself is going to be half of it. And since the height of this is 10, it's going to be about 5 inches. And so we can take the 1 inch up from this and then go up 5 inches, it should be at 6. And last but not least, for this bottom shape here, it's going to be 0.5 inches above. Okay? And then this is where we go ahead and start multiplying these two together to get into this column. So we're going to have 115, 11.5 times 10. Then we're going to have 60. And then last but not least, this should be 2.5. And we add those together, this should be 177.5. And I don't necessarily trust my mental math, so I'm going to go ahead and calculate it out. 115 plus 60 plus 2.5. There's no shame in checking your work like that. I'd rather you do it right and, than try to prove something to yourself and do it wrong. So, YC times A. So therefore, the YC for the entire shape is going to be equal to 177.5 divided by 25. And that's going to be inches cubed divided by inches squared. So hopefully you can see that'll give us a total unit of inches. So we'll take the 177.5 divided by 25. We're going to get 7.1. 7.1 inches. And that's actually not the final answer, but I boxed it anyway because it's something important. So now that we know the location of where this is, XC is going to be located at that height. Now we need to know what the second moment of area, or the area moment of inertia of this beam is in relation to this. And so that's where another formula we have, and this is going to be given in your formula sheet actually. I don't have the formula sheet printed out, but on my computer here I have it where it says section properties. This is what it gives us. So Ix is going to be equal to the sum of all the Ix's of each individual shape multiplied by the area of each shape and the dy, which I'll explain what that is a little more, the distance from the axis squared. So hopefully that didn't make you too dizzy moving you there. I'll go ahead and write that down below. So it's going to be equal to the sum of Ix plus the sum of area dy squared. And just the dy is squared, not the area. Maybe a little parentheses around that will help. But essentially what the area times dy, the Ix is the second moment of inertia of each of the individual shapes by themselves. The area times the dy is trying to take into consideration their distance from the x-axis. So if it were located on the x-axis, the area times the distance, and the dy is the distance of the centroid to the x-axis. If it were located on the x-axis, then that would be 0, which makes sense because it would be on the x-axis, so the moment of inertia about it would be just that shape. But here, we need to account for the distance because the further it is from this axis, the more inertia it's going to have out here. It's almost like on this pencil here. If I were to have a weight right in the center, I can move the pencil no problem. But if I put the weight on the edge of it, maybe if I did it like this, on the center it moves no problem. But if I put my finger on the edge of it, then it gets harder to. So you can kind of take that almost like you were a weight or just momentum on the wings. So we've got that. So what we need to solve for now is we need the Ix for each of these. So we can go ahead and put that in. Ix and give some space for that. We need area, we have area. And we need dy, which I'm going to go ahead and write absolute value because we're squaring it, so it doesn't matter what the sign is. And dy, and then we can take a times dy squared over here. Okay, and so another formula is Ix. This one actually was not given in the formula sheet, and it looks like it wasn't given in the problem here. So if you're doing these problems, it's always important maybe memorize the equation, the equation for the second moment of area for a rectangle. And so the equation's not too bad. For a rectangle, it's going to be 1/12, and since we're taking x in relation to the x, it's going to be base times height cubed in relation to the x-axis. Okay, if it were to the y, it would be height times base cubed. But base is the bottom part, and height is the top part here, if we were looking at this shape. So we'll go ahead into each of our shapes. For shape 1, our Ix will be 1/12 times the base is 10 inches, and the height is 1. We'll take that cubed, and I'll just go ahead and calculate it out. 10 divided by 12 is equal to 0.833. Next, we've got 1/12 times a base of 1 inch and a height of 10 inches cubed. That's going to be 10 inches cubed, or 10 cubed is going to be 1,000 divided by 12, which is going to be 83.3. And lastly, we're going to have 1/12 a base of 5, and a height of 1 cubed. And that should be half of what this first one is, which is 5 divided by 12, 0.417. Whoops, 417. So we can go ahead and add those all together. Take the, and the sum we get is 84.583. So that's the sum of all of our y-axis. We've got part of our formula found. Now we need the dy, the distances from the centroids to the x. So you could go through and find the centroids and then go ahead and calculate the distance out. But we know what this yc is. We got yc is equal to, as we found before, 7.1 inches. And we already know the locations of the centroids of these in relation to this bottom axis. That's in this here. So in order to find what the distance is from the centroid to this, we can just go ahead and take the centroid in relation to this bottom axis and subtract the 7.1. And so for the first shape, for area 1, we've got a YC of 11.5. We can go ahead and subtract 7.1 minus 7.1 is going to be 4.4. Next, we've got 6 minus 7.1. This is where the absolute value comes in handy. And that should be equal to 1.1. And then lastly, we've got 0.5 minus 7.1. And that'll give us 6.6. Okay, and then last but not least, we want area times dy squared. And so y here, or I'm sorry, dy right here, area there. So this is going to be equal to 10 times 4.4 squared, which is 193.6. Next, we've got 10 times 1.1 squared, which is, well, I'll go ahead and write that out. 1.1 squared is 12.1. And then we've got 5 times 6.6 squared, which is 217.8. So we go ahead and add these all together. 193.6 plus 12.1 plus 217.8, and we get 423.5. And then the values for these is inches fourth. As you can see in our equations here, base times height cubed, that's inches cubed times inches, inches to the fourth. This is again inches, and this is also inches to the fourth. That's inches squared times inches squared. And so overall, IXC is going to be equal to, let's see here, 84.583 plus 423.5. And that is 508 point, let's say 1 inches to the fourth. And again, I'm going to reiterate, I don't believe I have the solutions for these, so this could very well be the wrong answer. But this is kind of the way I would go about solving it myself. Hopefully I know it well enough to be able to convey it to you guys accurately. If not, and you guys call me on something bad, you can always email me or leave a comment down below. Otherwise, just let me know. You know, I'm not perfect. You know, nobody's perfect. And yeah, just let me know if there's any issues that I need to correct. So anyway, that's our solution for A. Part B now is determine the height H, this height here, of the rectangular beam such that the second moment of area of the two beams are equal. So we want IXC of this to equal IXC of that. And as you can see here, they drew XC of this rectangle right down the middle of it, smack dab in the center. And so that means we don't have to take into consideration the area times the distance from that. We can just assume it to be in the center. And so ultimately we want IXC to be equal to 508.1. We're looking at this. That means we want 1/12 times the base times height cubed to be equal to 508.1. And going even further, it's 1/12 times the base they gave us as 5 inches times the height cubed is equal to 508.1. We'll go ahead and calculate what h is. So we've got 508.1 divided by, and then in parentheses I'm going to say 1/12 times 5. Just taking this to the other side there. And we get 1219.44. We can go ahead and take the cubed root of that, because it's h cubed, 12.1219.44. The cubed root of that, we get h is equal to 10.68 inches. And that's our next solution, our next answer. So for part B, h is 10.68 inches. Now, last but not least, it says, when the design criterion is use the lighter beam, which beam should the designer use? Support your choice with numerical values and a brief explanation. Well, having to explain it's kind of lame, but we'll do our best shot at this. Just section this off. So this is where we need to calculate the areas of each of these. Well, we already have the total area for the I-beam. So I'm going to go ahead and write I-beam. And the total area for the I-beam is 25 inches squared. Next, we can go ahead and, take a look at rectangle. Rectangle. Or I guess you could draw it like that rectangle beam. But rectangle beam. And this is going to be base times height. Well, the base is 5 inches. And the height, as we found in part B, is 10.68 inches. And that's going to give us 5 times 10.68 is equal to 53.4 inches squared. And so, using those, and we want to find the lighter beam, this is where we have to reason through, and this is kind of some engineering logic. Well, looking at these two areas here in the cross-section, we should be able to see that the I-beam would be the lighter beam. And that means to get the same amount of, or the same second moment of area, the I-beam does a lot more with a lot less material. And that should be kind of prevalent when you take a look at the cross-sections here. As you can see, the I-beam is pretty doggone skinny. You know, it doesn't have a lot of material in the cross-section, whereas the rectangle here does have a lot of material in this cross-section. And so you can just look at it that way. But ultimately, by using our numbers, this has half the area of steel, or I'm sorry, concrete? I guess it doesn't say. Has half the area of material in the I-beam as the rectangle does, a little less than. And using that, if we were to make it, or expand it out across the entire beam of the same length, we therefore find that the weight of the I-beam would be less. And so doing that, we should be able to see that the I-beam is lighter. And so therefore, they should choose the I-beam. As far as writing up an explanation, you can kind of say something along the lines of what I said. You could say something about how the I-beam has less area in the cross-section, which that means if you expand it out along the entire length, it would have less volume and therefore less mass or weight overall. And that'd be the lighter beam. But yeah, here's how you solve a problem. These centroid problems are not very difficult, just as long as you know what the equations are, which are this equation and this equation are both in your, these two equations, are both in your equation sheet. This equation is one that might be given to you, might be something you want to memorize. So I would definitely take the time to memorize this for a rectangle. If you can. For weird shapes like circles or triangles or anything along those lines, they'll typically give them to you. I'm not sure if you'd find them in the exam or not, problems that involve those, but if they are involved, they would give the values to you, or the formulas. But definitely memorize for a rectangle. Otherwise, that's how you solve these problems. If you have any questions, let me know, and good luck on your exam and good luck studying.